Let's take a look at another type of problem that involves these confidence intervals. Let me just rewrite here our confidence interval formula. X bar plus or minus z times our standard error. So far we've talked about two ways of calculating the standard error. One way uses the population standard deviation and divides by sample size. Since in most cases we're not going to have that population standard deviation, we estimate it using the sample standard deviation and then correct the denominator, substituting the square root of n for the square root of n minus 1. That gives us this formula right over here. In both cases, these are both ways of calculating the standard error. Which one you use depends on what you're given in the problem. Suppose we're given a problem, however, where we're not being asked to create a confidence interval for a mean, but rather for a proportion. So, in other words, let's consider this problem. Let's say that we're working for a candidate who is running for U.S. Senate, and we know that we've conducted a telephone poll of n equals 1,393 respondents, and we found that 752 of those respondents are voting for our candidate. We want to construct a confidence interval for this data. All right. What we're talking about here really is a proportion. We're not talking about, there's no means here. We're talking about a proportion. Right now, it looks as if 752 over 1393, that proportion is going to be equal to 54%. But remember, this is only one sample proportion. Out there in the world is the true proportion of people who are going to be voting for our candidate. Would this proportion be representative of the underlying population 95% of the time? So instead of relying on either this formula for standard error or this formula for standard error, we have to introduce a new one. The new formula looks like this. We're going to compute the standard error by taking the square root of the probability that our candidate is going to win, and there's a 50-50 probability, by the probability that our candidate is going to lose, another 50-50 probability, divide that by the sample size. All right? Actually kind of interesting here because there are a couple of different standard error formulas that you might use for this kind of proportion problem. The one in your book is not necessarily the most common one, but it is the most conservative. That is, it's going to produce the widest confidence interval that you could produce, and for that reason, you're more likely to include, the wider the interval is, the more likely it is that the true population mean proportion will fall within that interval. It's also a bit easier because we don't have to do an intermediate calculation. But at any rate, we're going to use this formula here for population proportion problems. Okay? So we'll use this for sample means, and we'll use this one here in the unlikely event that we have a population standard deviation. All right, so how do we solve this problem? Well, the basic structure of the Z formula is the same. The confidence interval is going to be population proportion that we're starting with. All right, in this case, it would be 54%. I'll write it out as 0.54, plus or minus our Z value. We're interested in the 95% confidence interval here, so we know that value is going to be 0.96. I'll put Z over there, and that is going to be times 0.5 times 0.5, which is always, by the way, going to be 0.25, divided by n. So in this case, in our example here, it's going to work out to 0.5 times 0.5 divided by 1393, and we get that over here. Okay, let's do that calculation. We're going to get 0.54 plus or minus 1.96 times the result of this over here, and that is equal to 0.01. So we have 0.54 plus or minus 0.01 times 1.96, and that's going to be about 3%, about 0.3, actually 0.026, but we'll call it 0.3. All right, so it's looking pretty good for our candidate here, because our confidence interval is given now by 0.54 minus 0.3 on the low end and 0.54 plus 0.3 on the high end. So we're going to get here 0.51, and we're going to get over here 0.57. So it looks as if in 95% of all the possible samples we could have drawn, it looks as if our candidate is going to be above the 0.50, the 50% that he needs to win this election. So that would be how you solve this kind of a problem.